Welcome to my 50th tutoring session in A-level chemistry. In this video, I'll explain the concept of isotopes and its importance. Kindly subscribe my channel, share, like, comment and watch the full video. Atom is the smallest unit of an element. It has a central nucleus that contains positively charged protons and electrically neutral neutron, with the negatively charged electron orbiting around the nucleus in its respective shell or energy level. Now, each subatomic particle acts as a unit, and when we consider the mass of each unit, we express in terms of atomic mass unit. So the mass of one proton will be expressed in terms of one atomic mass unit, that is equivalent to 1.673 in 10 to the power of minus 27 kilograms. Mass of one neutron will also be expressed in terms of one atomic mass unit, that is equivalent to 1.675 in 10 to the power of minus 27 kilograms. Mass of one electron will also be considered as one atomic mass unit, that is equivalent to 9.109 in 10 to the power of minus 31 kilograms. Now, when you compare and contrast the ratio of these masses, you will find that the mass of electron is nearly 2000 times lighter than that of proton and neutron. At the same time, when you observe the values very closely, you'll find that the mass of neutron is slightly more than that of proton. That is to say, neutron is slightly heavier than proton. So atomic number is the number of protons present in the nucleus of that particular atom, and mass number refers to the sum of protons and neutrons present in the nucleus of that particular atom. Let's understand this concept with respect to the carbon atom. Atomic number of carbon is 6 because you find 6 protons in the nucleus of carbon atom. Mass number is 12. Mass number is the sum of protons and neutrons. So in case of carbon, it is 12. The nucleus of carbon atom contains 6 protons and 6 neutrons, and hence the mass number 12. Atomic weight is slightly different from the mass number. Mass number and atomic weight, they are not the same. They are different terms because some atoms of an element contain different number of neutrons, and these are called isotopes. Now, protons determines the element's identity, while the variation in number of neutrons, it gives the isotopes different atomic masses. So atomic number for carbon is 6, while the mass number is 12. Naturally occurring carbon contains 3 different isotopes, C12, C13 and C14. And because of the contribution of these 3 isotopes, that you end up with atomic weight of 12.01 in case of carbon. So isotopes are different forms of an element that have the same number of protons but different number of neutrons in their atomic nuclei. So this means that isotopes of an element have the same atomic number but different mass numbers. So it is due to the variation in the number of neutrons which gives the isotopes different atomic masses. Like in case of carbon, you find C12, C13 and C14 isotopes due to variation in the number of neutrons. So since the number of protons determines the element's identity, isotopes of the same element have the same atomic number but different mass numbers. Though carbon exists in 3 isotopic forms, it does not lose its identity. The identity is retained because of the atomic number. So when you compare and contrast the C12, C13, C14 isotope, you'll find the atomic number is same, and therefore the identity of the carbon element is retained, though they exist in the different isotopic forms. Now, isotopes, there are two types. One is the stable isotope, other is the unstable isotope. Now, in case of stable isotope, now stable isotope has a stable nucleus with ideal or correct number of protons and neutrons. Like in case of the C12 isotope, it has a stable nucleus because the number of protons in the nucleus of C12 atom is 6 protons, and the number of neutrons in the nucleus of a stable carbon atom, that is C12 isotope, is 6. So here you find a balanced amount of protons and neutrons in case of C12 isotope, and hence it is stable in nature. So much of the world around us is made up of stable isotopes. And what about the unstable isotopes? Now, unstable isotopes, they have unstable nucleus. So these isotopes are unstable in nature because of their unstable nucleus. And why the nucleus is unstable? Because of unequal amounts of protons and neutrons. So there is no balance between the number of protons and neutrons. So greater the instability of nucleus, the quicker it will attempt to rearrange itself into more stable configuration. Like for example, in case of isotope of hydrogen, that is tritium, nucleus is unstable because in case of tritium, isotope of hydrogen, you find 1 proton and 2 neutron. So there is an imbalance in the number of the protons and neutrons, and therefore it tends to undergo radioactive decay in order to get rid of number of neutrons, additional neutrons. And after the decay, it regains its stable form with ideal or correct number of protons and neutrons, which is in balanced form. So if there are too many neutrons, the nucleus can spontaneously rearrange itself and throw out particles in the process. And that makes the isotopes radioactive in nature. So isotopes with unstable nuclei are called radioactive isotopes or radioisotopes. The greater the instability of a nucleus, the quicker it will attempt to rearrange itself into a more stable configuration. And this process is referred to as radioactive decay. So why do you find this decimal number in the periodic table, which is represented as relative atomic mass or relative atomic weight? And how do you calculate the relative atomic weight of an element? And let's try and understand this with respect to the carbon element and its isotopes. The mass number of carbon is 12, atomic number is 6. But why do you get the relative atomic mass of carbon in decimals? That is because of the natural carbon containing 3 different isotopes. So natural carbon contains 3 isotopes, C12, C13 and C14. And when you observe the nucleus of these 3 isotopes, you will find the number of protons remains one and the same, that is 6, while the number of neutrons, they are different. So it is due to the variation in the number of neutrons of these 3 isotopes, it contributes to the relative atomic mass to be represented in decimals, not whole numbers. So mass number of C12 isotope is 12, mass number of C13 isotope is 13, and mass number of C14 isotope is 14. So you'll find that the number of protons remain one and the same, that is 6, while there's variation in the number of the neutrons. So C12 isotope has 6 neutrons, C13 isotope has 7 neutrons, while C14 isotope has 18 neutrons. So it is due to the variation in the number of neutrons that gives isotopes, these 3 isotopes, different masses. And how do you calculate the relative atomic weight of carbon? You multiply the mass number of each isotope with its respective abundance, sum of these three values, and divide the whole thing by 100. And when you divide the whole thing by 100, you end up with the relative atomic mass of carbon, that is 12.011, which is in decimal, not in whole numbers. So now you know why the relative atomic mass of element is in decimals, not in whole numbers. It is due to the contribution of different isotopes of that particular element in the periodic table. And this is how you calculate the relative atomic weight of an element. And what is the abundance? Now here carbon 12 has an abundance of 98.89%, C13 has abundance of 1.1%, while carbon 14 has abundance of 0.01%. Now abundance is the percentage of that particular isotope present in the element. So in case of C14, its presence is very negligible as compared to C12 and C13. So abundance of C12 is more, as compared to C13 and C14. Now C12 isotope is highly stable because it has a balanced number of protons and neutrons in its nucleus. It has 6 protons and 6 neutrons. Well, in case of C13, it has 6 protons and 7 neutrons. The balance is slightly lost, 6 protons and 7 neutrons. In case of C14, the nucleus of that particular isotope has 6 protons and 8 neutrons. So due to the balanced amount of protons and neutrons in nucleus of carbon 12 isotope, it is the most stable isotope of carbon atom. C13 is unstable isotope of carbon atom with abundance of only 1.11%, and C14 is highly unstable isotope of the carbon atom, and its abundance is very negligible, and rarely you will find this particular isotope. So the abundance or the presence of that particular isotope depends on the stability. So if it is more stable, its abundance will be more. If it is unstable, its abundance will be less. So now you know the meaning of mass number, atomic number, and the atomic weight or the relative atomic weight. So carbon has an atomic number of 6 and mass number of 12, but an atomic weight of 12.01 because of the natural presence of some carbon atoms with a mass of 13, that is 7 neutrons instead of 6, and 14, where you find 8 neutrons instead of 6. So it is because of contribution of these three different isotopes of carbon that you end up with a relative atomic weight of 12.01, which is in decimal and not whole number. So the relative atomic weight of an element is the average atomic mass of its naturally occurring isotopes. And this is how we calculate the relative atomic weight of carbon. Isotopes have the general formula where X refers to the element, Y stands for the atomic number, and Z represents the mass number of that particular element. Now carbon and nitrogen, they are not isotopes. They are two different elements, because when you compare and contrast the atomic and mass numbers of carbon and nitrogen, you will find that neither their atomic numbers nor their mass numbers match. And therefore, they are two different elements. But C12 and C13 are isotopes of carbon. Why they are considered isotopes? Because when you compare and contrast these two, you'll find that atomic numbers match, they are the same, but the mass numbers are different. Similarly, bromine has two different isotopes, 79 and 81. And again, when you compare and contrast the atomic and mass numbers of these two isotopes of bromine, you'll find that atomic number is same, that is 35, while there is varying number of, that they have different mass numbers, that is 79 and 81. That is due to varying number of neutrons in that particular isotopes of bromine. So carbon and nitrogen are not isotopes, they are two different elements, while C12, C13 and Br79 and 81 are isotopes. So it is important to note that carbon and nitrogen are two different elements with different atomic and mass numbers. They are not isotopes. So this means isotopes of an element are the same atomic number but different mass numbers. Now the number of protons determines the element's identity. So in case of carbon 12 and carbon 13 isotopes, it does not lose its identity. The identity of carbon is retained, though they exist in two isotopic forms. Even in case of bromine, though it exists in two isotopic forms, that is 79 and 81, it retains its identity because the number of protons are one and the same in case of C12, C13 and Br79 and 81. And as we all know, the number of proton determines the element's identity. While in case of carbon and nitrogen, they are two different elements because atomic numbers are different. So definitely their identity will be different. And that is why they exist as two different elements. Carbon with 6 protons exists as the element, while nitrogen with atomic number of 7 is a totally different element. So the number of protons present in the particular element determines its identity and position in the periodic table. Now it is a variation in the number of neutron. It gives isotopes different atomic masses. So here are the examples of some of the isotopes of elements that you can find in the periodic table. So isotopes of hydrogen, protium, deuterium and tritium. Isotopes of carbon, C12, C13 and C14. Isotopes of chlorine, chlorine 35 and 37. Isotopes of bromine, bromine 79 and 81. In these four examples mentioned as isotopes, you will find that the atomic numbers are one and the same, while there is variation in the number of neutrons. That leads to their different mass numbers. So neutron has a vital role to play, and that determines the isotopes or isotopic form of that particular element. Now we kind of ignore the electrons in the atomic weight calculation due to their negligible mass. So electrons are nearly 2000 times lighter than that of protons and neutrons. And that is why we ignore electrons in the atomic weight calculation. So atomic weight and mass number, they are two different terms. So atomic weight is slightly different from mass number because some atoms of element contain different number of neutrons. These are called isotopes. They are in decimals, not whole numbers. And that gives the relative atomic weight. So what you see in the periodic table or the decimal values that you find in the periodic table is the relative atomic weight. So in case of carbon, the expected or the theoretical value is 12, but the actual value, that is the relative atomic weight of carbon is 12.01. And in case of chlorine, the expected value is 34. So you get this 34 from calculating the number of protons and neutrons, considering chlorine to be stable atom. But the actual value is 35.45. And where do you get this 35.45? because of the natural presence of some chlorine atoms with a mass number of 35 and 37. That is due to variation in the number of neutrons. And likewise, in case of bromine, the expected value as per the theoretical calculation it is 70, but actual value that you find in the periodic table is 79.90. And that is why, once again, due to the natural presence of some bromine atoms with a mass number of 79 and 81. It's again due to variation in the number of neutrons. So remember these 2 points. Atomic number, which is the number of protons present in the nucleus of an atom, it determines the identity of an element, while neutrons, they play a vital role in determining the isotopic form of that particular element. So relative abundance of these isotopes refers to the percentage or proportion of each isotope found in a naturally occurring sample of chlorine. Now to calculate the relative abundance of isotopes of chlorine, so let's consider a sample of 100 atoms of chlorine in nature, and we will be using the known isotopic abundance of chlorine, that is chlorine 35 and 37, to determine their respective percentages. Now you'll find the relative. Now what is the source of these relative atomic weight? Say for example, you want to find out the relative atomic weight of chlorine. There are two sources. One is you can refer the periodic table and you can get the relative atomic weight of chlorine. And the other source is the mass spectral analysis. By analyzing the chlorine sample using a mass spectrometer, you can get the relative atomic weight. So one is you can get the information from the periodic table or from the mass spectral graph. So let us consider a sample of 100 atoms of chlorine in nature. So in nature, out of 100 atoms of chlorine sample that we have considered, 25 atoms are existing in the 37 isotopic form, while 75 atoms are existing in the Cl35 form. So 25 atoms in the 37 form and 75 atoms in the 35 isotope form. Now calculating the relative atomic mass from mass spectra. Now chlorine Cl35, it has an abundance of 75.77%, while chlorine 37 has an abundance of 24.23%. Now you may ask me, where do you get this abundance value of 75.77% and chlorine with the abundance value of 24.23%? Now this you will get it from the mass spectra of chlorine. So you can calculate, theoretically you can calculate the relative atomic weight of chlorine using the formula that I've explained previously. So you multiply the relative abundance of that particular isotope with the mass number and sum up the values and divide the whole thing by 100. That is how you end up with relative atomic weight of chlorine, that is 35.48. So this is the theoretical concept or theoretical calculation. Now practically, you can also get it from the mass spectral analysis, which is a plot of relative atomic weight on the x-axis. It's nothing but the mass to charge ratio, and on y-axis is a plot of abundance or the relative intensity in percentage. So you get two peaks, C35 peak and C37 peak. That is CL35 and CL37. The one peak is more intense than the other. This is because the less intense peak is due to their less abundance. They are less stable and less abundant. And that is why the peak is less intense. While the CL35 peak is more intense because it is more stable and more abundant and therefore produced to a greater extent. Let's consider the mass spectrum of chlorine atom and chlorine molecule in much more detail. So you get two peaks. One is the intense peak, one is a more intense peak, and the other is the less intense peak. The more intense peak is due to Cl35 isotope and the less intense peak is due to Cl37 isotope. And that is due to a difference in their stability and abundance. So in a mass spectral bar graph, the x-axis represents the mass to charge ratio, while the y-axis represents the relative abundance of ions detected at each mass to charge value. Now this is how you get the relative abundance of that particular isotope. Now in case of Cl35, now if you go by the x-axis, you will get their relative atomic weight, that is 35. And if you go by the y-axis, you will get their relative abundance. So here it is showing as 77.7%. Again, for the Cl37 isotope, going by the, so you get that 37 based on the x-axis. As you go by the x-axis, which is nothing but the relative atomic weight. And if you go by the y-axis, you will get the relative abundance, which is approximately around 25%. And remember, the chlorine element, it doesn't exist in the atomic form, but instead they exist in the molecular form as diatomic molecules. Halogens in general, they do not exist in the elemental form, but they exist in the molecular form, that is as diatomic halogens. And that is why, in addition to the 35 and 37 peak, you also get three more peaks, values of 70, 72 and 74. And these three varying values, so molecule is same, that is chlorine molecule is same, but you get three different peaks because as you can see, there are three different possibilities. Both the atoms can be of 35 isotope, both the atoms can be of 37 isotope, or one atom can be of 35 isotope and the other atom can be of 37 isotope. So due to these three different varying probabilities of the respective isotopes, you get three different molecular peaks for chlorine. Now detailed explanation and further theoretical concepts about the mass spectral analysis will be discussed in my forthcoming video on mass spectroscopy. And that is how you get the relative atomic weight of chlorine in decimals, that is 35.45. So atomic number of chlorine is 17, while the relative atomic mass is 35.45. And this is because of the contribution of two different isotopes of chlorine, that is 35 and 37. And when you consider their average atomic mass, you end up with decimal value and not whole number. So mass spectrum can be represented either by a stick plot or a bar graph or can also be represented by a tabular form. So in the tabular form, you've got two columns. One column representing their relative mass, and the another column represents their relative abundance. So mass spectral details of particular element, the molecule can be represented either by a bar graph or tabular form. So the peaks on the graph indicate the presence and abundance of different ions corresponding to specific isotopes or molecular fragments. So here the peaks, what you find in the mass spectrum of chlorine, they not only indicate the presence but also the abundance of different ions corresponding to specific isotopes or molecular fragments. So here are the isotopic composition of some common elements. And carbon-12 isotope is widely used as a reference standard because of its stability, non-reactive nature, its abundance in nature, and its well-defined atomic mass. That is because of its consistency with a value of 12 atomic mass units or 12 unified atomic mass units. And these are the several factors that contribute to its suitability as a reference standard. And you can deduce the number of carbon atoms in a compound using the n+1 peak and this particular formula. And further details will be explained in my forthcoming video on mass spectral analysis. Now the isotopes of hydrogen are protium, deuterium and tritium. Hydrogen has a mass of approximately 1 atomic mass unit. Deuterium has a mass of approximately 2 atomic mass units. Tritium has a mass of approximately 3 atomic mass units. And the relative abundance of hydrogen is 99.99%. Deuterium is 0.015%, while tritium is negligible. It's almost zero. And carbon-12, it's a mass of exactly 12 atomic mass units. Carbon-13 has a mass of approximately 13 atomic mass units. Carbon-14 has a mass of approximately 14 atomic mass units. And the abundance of C12 is 98.89%. Carbon-13 is 1.11%, while C14 is negligible. And talking about the bromine, bromine 79 isotope, it's a mass of approximately 79 atomic mass unit. Bromine 81 isotope has a mass of approximately 81 atomic mass units. And the relative abundance of Br 79 and 81 is almost equal. 79 is around 50.69%, while Br 81 accounts for nearly 49.31%. Chlorine has a mass of approximately 35 atomic mass units, and chlorine 37 has a mass of approximately 37 atomic mass units. And their relative abundance are in the ratio of 3:1. So around 75% of Cl35 isotope and 25% of Cl37 isotope. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.